MAE and MEC 3456. Today we're going to be having a quick look at Taylor series. Now I'm sure you've all seen Taylor series before, and I'm going to go through this because Taylor series are central to much of numerical analysis. You're going to need to use this time and time again in this unit, so I thought we'd go back to the basics and make sure that you understand where it comes from and how to use it. So, the starting point for deriving the Taylor series is we need to first of all imagine that we know the value of a function and all its derivatives at a point. We'll call that point x0. So, if we have our little function here, it looks something like this. We have some value x0. We're saying we know what the function value is here. We know what the slope of the function is there. That's the first derivative. We know what the curvature of the function is there. That's the second derivative, and we know all of the higher order values. So, if we know that, then the question is, I want to go to a different point. Let's call that x. How can we estimate the function value at this other point? That's what Taylor series are all about. Okay, the starting point for the analysis then is to assume that we can write the function value at some point x as a polynomial, effectively, with an infinite number of terms. And we're going to write this as the function value at x, in other words, this function value at the top corner just there, is equal to c0 plus c1 times x minus x0 plus c2 times x minus x0 squared, and so on. Okay, it's just a polynomial, but this goes on infinitely. If we make that assumption, then, the question becomes, what are the coefficients ci equal to? If we can figure that one out, then we've derived the Taylor series. Okay, so let's write out our equation again for f of x as a polynomial. We're going to call that equation 1. If we let x equal x0 in this, we can see that all of these terms, all the x minus x0s, are 0. And we're simply left with c0 is equal to f of x0. So we've found our first coefficient. Okay, let's take the derivative of equation 1. So f dashed of x is equal to, well, the derivative of the c0 term is going to be 0. The derivative of the c1 term is just going to be c1. The derivative of the c2 term is going to be twice c2 x minus x0. Derivative of the c3 term is going to be 3c3 x minus x0 squared, and so on. Let's call that equation 2. So we've just rewritten equation 2 at the top here. Let's let x equal x0. And we can see then that the left-hand side is df dx at x0 is equal to, again, all of these terms are going to drop out. And therefore, c1 is equal to df dx evaluated at x0. And remember, the basic assumption, our starting assumption, was we knew what the function and all its derivatives were at this point. So we now know what c1 is equal to. We're going to go through a similar process. Let's take the derivative of equation 2. Okay, so the c1 term here drops out, the c2 term becomes a constant term, the c3 term becomes the power of x minus x0, the first power, etc. That's equation 3. We let x equal x0 in this expression. So again, all of these terms are going to drop out. And it's quite easy to then show that c2 is equal to 1/2 d squared f dx squared evaluated at x0. And again, we know what this is. We're told we know this. We can keep on going, take the derivative of equation 3, but I think by now you should see the pattern. So let's go back to our original assumption that we could write f of x at any point as this particular polynomial. We know what the c0, the c1 and the c2 are. We've just calculated them. c1 is f of x0, c0 is f of x0, c1 is df dx at x0, etc. And this then gives us the Taylor series. It says that f of x is equal to this long expression here. Now, more often it's convenient to write x is equal to x0 plus delta, where delta is just some kind of increment in distance. So, just using this expression here in our Taylor series in the previous line, gives us that f of x naught plus delta is equal to f of x naught plus delta df dx evaluated at x naught plus the higher order terms. You should remember this. You need to remember what the Taylor series looks like, and you need to feel very comfortable in using it because you will need to use it many times in this unit. And I recommend that you understand how this derivation works and that you can do it yourself as well. Now, Taylor series, as we've just described them, are for a function that's a function of only one variable. There's nothing whatsoever that stops us from having functions of multiple variables. For example, here I've written the Taylor series equivalent for a function of two variables, f of x and y. So f of x plus alpha and y plus beta, where alpha and beta are increments, is just equal to the function value of x and y, plus alpha times df dx, evaluated at the point, plus beta times df dy. Those are the first order terms, then the second order terms. There's three terms, alpha squared on 2 times d squared f dx squared, plus alpha beta d squared f dx dy, that's the middle term here, plus beta squared on 2 d squared f d squared y. The nth order term looks something like this, where we have a sum of different products with alphas and betas raised to different powers, multiplied by the different derivatives. They'll all be nth order derivatives. I don't expect you to remember this formula, but I do expect you to know how to use it. Now, of course, I've written it here as f as being a function of x and y, but you can replace x by y or t or anything else that you like. Okay, x and y are not sacrosanct. You can use any variables you like, and indeed you may need to. So, key points from this little video then are Taylor series. Where does the Taylor series come from? In particular, how do you derive the 1D, but also what does the multidimensional Taylor series look like? We only looked at 2 dimensions, and we won't need to go to higher orders in this unit. So, in the next lecture, or the next little video, we're going to have an overview of error, and the one after that will have a brief MATLAB refresher. So that's all this time.